All right, so let's get started. So welcome everyone. Thank you for coming to this public seminar and organized by BIM Education New Zealand. And today we are very fortunate to have Professor Rafael from Technion Israel Institute of Technology. And his research focus on building information modeling, link construction, and the synergies between them. So currently, he's also the director of the National Building Research Institute at the Technion and the head of the Virtual Construction Laboratory. And as we all know, Rafael, he is the very famous, the lead author of the BIM Handbook, currently in its 3rd edition, and the lead author of Building Lean, Building BIM, Changing Construction the tidal way. So this is just a brief introduction of Rafael, and now the stage is yours.
Thank you very much, Zenang, and thank you very much for the invitation. I know that this took a long time to put together, and I'm really, really pleased to at least be here in New Zealand virtually. It would be great to visit. I have done so in the past and have many close friends, particularly in academia in New Zealand. Some of us have joined. So I thought that I would try to give a sense of what future trends might be in BIM technology and process. And being a researcher in the area, what I will try to do is to give a sense of what's happening in research institutes, in research labs, more than in technology companies. I can't necessarily speak for commercial BIM vendors, so I will try to give you a sense of what the ideas are in academia, and particularly speak from personal experience in our own lab here at the Technion. I thought that I would talk a little about the essence of what we're doing in building information modeling, and I'll try to keep myself to an hour or thereabouts so that we have time for questions. And I do appreciate that it's late in the evening in New Zealand, and so we'll try to finish in a reasonable time. So really, building information modeling is a tool, if you like, a set of tools for communicating information about buildings and about building as a verb as much as buildings as nouns, as a noun. So we're trying to conceptualize, to communicate, to collaborate, and also to document. And those are, I think, the 4 purposes or things that we achieve. And fundamentally, we are trying to communicate ideas, cognitive ideas from one person's mind to other people's minds and in return. And one way of measuring whether we succeed or to what degree we succeed is to ask how similar are each of those people's concepts of the building that we're trying to build or of the process that we're trying to plan. We like to bring them into close alignment as possible so that we all understand and we're all on the same page. And so this has been a challenge throughout history for anyone trying to build anything. And I think it's obviously central to human development as social animals that our major advantage over perhaps other animals is that we're able to collaborate. And collaboration requires coordination and communication. So through history, in terms of building things, we began by various methods of verbal and other communication, but then we've had really, I would say, 3 major technological advances. The first being descriptive geometry, the second being computer-aided drafting, and the third being BIM. And as we know how things collapse in scales of time, we can ask the question, well, what comes next? Will it be just some sort of more sophisticated BIM, or perhaps is there something else coming down the line? So let me just take a moment to look at these 3 things: descriptive geometry, CAD, and then BIM. So I'll start with that historical context, and then we'll talk about current practice and where we are now. What we don't have and what our problems are still today. And then I think I'll touch on technology and process resources that we have available that might help us address some of those problems. And that will lead me to the future trends in BIM technology and process. Okay, so launching right into it. I mean, we all know that the age of the master builders, particularly in Europe, but in other places around the world too, were a time where communication was rather difficult. Writing and paper were not that common. And as you can see on the top right-hand side here, oftentimes the practice was to prepare a room, prepare a floor of clay or of other soft earth, and then draw out things in the clay and discuss that in that room, go out and build the thing. And when you needed a new drawing, you would come back, sweep the floor, clean it up, and then start again. That was sort of the graphic communication technology. And that gave way in the 1700s, in the 18th century, to two key inventions that supported that communication, both descriptive geometry and parallel projection versus perspective views. And this really was quite a technological breakthrough. You can look it up in the link I've given here of Gaspard Monge in France, who wrote up a lot of the, summarized a lot of the understanding of what descriptive geometry was. And these are things that allowed people to do drawings of this kind. Although these temples are from much earlier, the drawings of them are from the 1700s. And you begin to see in the literature for the first time true parallel projections, so that objects are considered to be at an infinite space, and you're considered to see with parallel projection rather than perspective. And that allows you to do cross sections and facades and other things that relate one to the other. And descriptive geometry, of course, also allowed people to prepare front views, side views, top views, and isometric views, all of which were unique in that they could be measured. You could measure them on the paper, and to scale, of course. So we have things like these parallel projections. You see on the right-hand side an isometric view where the dimensions are in proportion to what they are in reality. So that you were able to take a scale rule and work off something like that. On the left-hand side, a cross-section of the same building. And here quite clearly you see how the cross-sections, the dimensioning and so on became possible and led to regular drawings. And that's, of course, in contrast to the parallel projection, the perspective projection of the same building, which would look like this, and where naturally we see things in distorted form, and we could not measure or really use this for construction drawings. And then of course, people took the technology of parallel projection and descriptive geometry and the layout of mechanical drawings and applied them with computers. So we got CAD, computer-aided drafting, which fundamentally took a mouse and screen to replace the pen and paper. But from a conceptual point of view, it's pretty much the same thing. Of course, it comes with huge efficiencies and accuracies of dimension, but not a whole lot more. And then we take a step forward, at least in imagination, if not in practice. This is a piece from 1962, which I guess I won't surprise too many if I tell you is the year I was born. But it's a piece that was done for the United States government, for DARPA. And Douglas Engelbart in this paper wrote about a future intelligent architectural agent, computer agent. 1962, a time even before punching cards. So he's talking here about how the architect can move a pointer on the screen and give instruction to his artificial intelligent clerk to show him a perspective view of the hillside building and ask the clerk questions about, does the building meet code, and all sorts of other really wonderful things being imagined in 1962 as the future of intelligent computing. And then when you have that perspective that this kind of text was already available at that time, you take a step forward, 13 years forward to Chuck Eastman in 1975, writing about a building design system, a building description system, which again is a computer system to design consisting of interactively defining elements, again, with a mouse and a screen, automatically deriving plans, isometrics, perspectives from the same description of elements. And I won't go through all the text, but you can see that this is absolutely prophetic in the sense that almost everything we understand now as building information modeling systems is described here in 1975, something that took really more than 25 years to become technologically practical in the industry. Now we sort of more or less take for granted that we can do this kind of thing where not only can we model things in building modeling, we can merge it with GIS systems, merge it with intelligent survey systems, do system comparisons, clash checking, all kinds of weird and wonderful things that are pretty much accepted practice throughout industry now. So we've come a very long way in a very short time. And I think this image of a hospital in Denver, Colorado shows the same thing. You have highly complex building with many, many systems, and we are able to model them entirely and perform fairly effective coordination and clash checking and so on for those models and drive the production from the models. You could think of this kind of progression from past to present in this way. This is from the past publicly accepted standards from the UK from, say, 8, 9, 10 years ago, where they started to lay out this idea that we have level 0, 1, and 2. CAD, of course, being level 0, and then BIM, federated BIM models as being level 2. And again, with a look forward to level 3. And level 3, they broke down in the standard. This has now become updated a number of times, but you see that this IBIM, intelligent BIM thing, is still something that sits in the future, not in the present. Whereas these ideas of IFC and exchange and interoperability, some of them are, they're very well developed. So level 3 is not one single thing, but it's perhaps how they viewed in 2010, how things would develop. The industry, I would say, is largely sitting at level 2 with a bit of IFC and interoperability thrown in. So that plays out as these federated models where we have architectural views, structural views, mechanical systems, and each of those run in their own silo, and they're brought together from time to time to compare, to check, to coordinate, and then back to additional cycles of coordination and design. And most of that now is crystallized in the processes described in ISO 19650. So that's become standard practice for industry, and I think it's fairly well recognized. The use of common data environments for storing files, for then comparing files, and the procedures for working backwards with BIM coordination formats and checking things and revising those components of the federated models. You can see it here. This is from a building in Singapore called Maple Tree. Again, 2015, 2016, fairly recent, but already this idea of combining federated models is well established. And of course, we've been dealing for some years with this problem of interoperability. Some years, I mean, something like 30 years. And we see clearly that even today, we have multiple software working on BIM in one way or another. They serve a great number of purposes, but it's not coincidental that things have evolved in this way, that they've developed in this way, in the sense that different professions in the building industry have very highly specialized ways of working. And so those specialized ways of working lead them to have different conceptual understandings of the way buildings work. And that means that the software which embeds a discipline-specific ontology for each discipline have to be different. They work in different ways, they respond in different ways, and they allow the objects within them to behave in different ways, which means we have different software. And then the challenge is to communicate information from one to the other. And that's challenging because the schema, the ways we understand the information are different. Not to mention that we have confidentiality, privacy, legal considerations, and other things, and provenance of information and liability. So right now, most of the solutions we have fall into one of three categories: either direct interfaces between applications, where somebody writes an export for a particular software. We also have situations where some of these multiple or multitude software applications have versions which can be embedded directly in a BIM authoring platform. And we have common data schema, like the open schema of IFC, which allow you to export and import from a neutral, widely accepted standard schema. So you have things like this kind of flow, where we use IFC within a workflow that begins mostly with architecture, export of IFC files, and then importing to structural software, mechanical software, others, export again, clash detection in some sort of special software, and then repeat the cycle and so on. And as I said, that's the IFC itself is in ISO 16739, but this cycle of checking and delivering information and so on is encapsulated in ISO 19650. And so it's become fairly well established. Countries and companies have, and projects for that matter, have BIM execution plans. And these are fairly well established, but they're not without their problems. And those mostly have to do with the fact that we have sequential design. Things are done in series rather than in parallel. We have very late coordination in the process, and it's iterative. And we have standalone files, which are really don't contain much information beyond the very narrow scope of each particular profession. So we can ask, what kind of problems then do we still have? And I'm going to list 3 or 4. The first one is this thing that we know from the old days, let's say, that we still have this fragmented nature and the idea of passing things over the wall from one step in the process to the next, or from one profession to the next. And in general, a lot of rework, a lot of iteration, lengthy times for project development and construction. And in the end, often clients who don't necessarily get what they expected or what they wanted. And with some of the problems listed here. And these are not new problems, but they seem to be fairly persistent. And as I said, the interoperability is to an extent solved, but not entirely. And we have these problems of reconstruction and handing over and loss of information, especially loss of semantic content. And what do I mean by that? What I mean is that, if you consider a Revit model, then within the Revit model, the objects have certain behaviors which are constrained by the way the software is built. Columns support beams, beams support slabs. If there are overlapping volumes in a structural model, and the software is intelligent enough to do joins of that geometry and to take care that it's not reporting double quantities for volumes that overlap. By the same token, in an architectural model, it may mean that there is no meaning to a window outside of a wall, and so they don't exist outside of walls. And that kind of thing is a kind of design intent, a design understanding of behavior is maintained automatically by the software. But then you come along and do an IFC export, and you lose a lot of that. So you lose the parametric geometry, you lose the aggregations, the parts of sometimes. You may lose the functional relationships, but in particular, you lose the constraints, the parametric constraints. And by parametric constraints, I mean exactly those things that dictate the logic of the way the building works for each particular design professional domain. Let me make it even more, let me stress this even more, because it's not only that you lose semantic content that's in BIM software, but sometimes there are aspects of semantic content that was never in the BIM software to begin with. So, and that's particularly across disciplines. Within disciplines, software does it quite well, but across disciplines, it doesn't do it very well at all, if probably not at all. Here you see on the left, mechanical engineering, electrical and plumbing model, which has a radiator, and that radiator is mounted on a wall. And the fact that that radiator is attached to or mounted on the architectural wall is something that is entirely implicit in the models. We understand it when we observe that model, or when we do a clash check or bring a federated model together, but we understand it by context, not by any kind of explicit information that's present in the models. And what that means is that we as designers can understand that, but the computer has no chance of doing anything intelligent based on the obvious design intent relationship that we mean for that radiator to be mounted on that wall. And what I mean by that is, if you were to move the wall or change the thickness of the wall or something of that kind, it would be only natural that the radiator should move in a corresponding way. The same goes here on the right-hand side for the structural wall. We have here a precast piece, and the core of the wall is obviously in the structural model is serving this architectural wall. And so it corresponds. And there again, any kind of edit that we would make to the architectural wall, we would expect to see reflected in the structural wall. And that kind of thing, again, is entirely left to the human designers to control. Now, I don't want to imply for a moment that we want to remove human control. No, we want to maintain that. But there is a great amount, and I'm sure many of you in the call, in the webinar are, you're doing this as a professional day to day, and I'm sure you're aware of the headaches involved in maintaining consistency across different disciplines in the models, and the amount of time you spend correcting models or changing things when some other discipline has made a change. So you would at least expect that this kind of change would be accommodated in the software and at least presented to you as something that you could authorize or reject, but you wouldn't have to do the drudgery work of actually moving the stuff or editing it or changing its dimensions and so on. So I could sum up like this and say that the way we work with multiple federated models is here to stay. That's because of the professional specialization that we have, and that's not likely to change. The fact that models lack semantic content is a block, because it limits the degree to which the software can actually respond and do things that we expect it to do. Concurrent design, as a result, is still very difficult, and that's part of the reason why we have sequential design. We would rather wait until the architect does everything before I do my structural design, because then I assume I will make fewer changes and I'll have less drudgery and less need to maintain consistency when things change. Managing design variations is very cumbersome. If we have different versions of the same thing and we're considering different alternatives, there might be minor alternatives within a whole building, but it requires us to save different files of the whole building, which is truly cumbersome. And collaboration relies on imperfect interoperability, as I've discussed. And finally, the file-based storage, the technology that we use is really quite difficult, because that dictates our difficulties with version changes and consistency maintenance and with relationships across models. So what next? What might we do to address some of those problems in the, let's say, the medium and the long term? Well, let me give you an example of the kinds of things that we could imagine we might be able to see. And what I'll show you here is a piece of work from a PhD student here in our lab, who is employed by Trimble in Finland at the Trimble Development Center, and very much engaged both in research but also in their product development department. And we ask the question like this: let's imagine we have an architect who is looking at a building, and there is a flaw in the building, and the client says, actually, and I should say in parentheses, this is a real case. This is the Trimble headquarters building, and this was an exact design change that had to be made. So the users of the building said, well, actually, we'd like to have a connection between the third and fourth floors at this point. It's an open plan office, so we need a staircase. And the architect says, oh, okay, I'm going to go ahead and imagine I open up a hole in this floor, and that rectangular hole is going to be filled by a staircase, an open staircase, which people can use to move from third, fourth, fifth, and sixth floors. And so that's the architect's idea in terms of the space planning. And then what happens is you can imagine that the system, the software says, oh, this will cause a design issue with a structural model. This is the intelligent agent, if you like, looking over the shoulder of the architect and saying, I'm intelligent enough to tell you that this is going to cause an issue, and let me show you what the issue will be. So now the architect says, okay, let me review this. So some conflict's going to happen. Let's check it out. So the system then says, okay, let me explain to you what's going on here. Here's the floor of the building, and here is the slab area where you want to change. And if I open up the model in this area, there is a hollow core slab there. And if you cut it in that direction, you're going to cut through all of those hollow core planks, which is a real challenge for the structural engineer to cope with. So what would you like to do? So this is the problem. So the architect then says, okay, I understand the design issue. Let me raise this with the structural engineer. Now we imagine that the structural engineer is some other location opposite their software, and they now receive a request. And it says, oh, the architect is busy considering making this change to this building model. Would you like to review, because they have an issue? And the engineer, apart from thinking, well, I can charge for these hours, is going to say, okay, let's review this. And again, the system displays to the engineer what the potential problem is and what the architect would like to do. And then the engineer would say something like, oh, okay, interesting. How about, instead of doing this, we rotate that opening by 90 degrees so that it's parallel to the thing. So this is the system suggesting a fix. And the engineer might say, okay, that's much better idea, because that's going to be much easier to support that missing plank or make the hole in the area of a hollow core plank. And it's going to then suggest that back to the architect. Now, if we go back to the architect screen, they might receive that kind of communication from the structural engineer, who might say, yeah, you know what, how about doing this? And the architect could then say, yeah, okay, I'm happy to do that, and go ahead and accept that kind of fix, and not necessarily in the same place, but adopt the basic principle. And that kind of consultation, apart from being online, could be assisted or aided by an intelligent system that was able to determine that conflict and raise it as an issue right at the beginning, rather than waiting for another month of design cycle and a great deal of work on the part of the architect before realizing that this was not going to fly. So if we'd like to have that kind of cross-disciplinary intelligent behavior that expresses design intents, what we really want to do is utilize, I think, some of these opportunities. Concurrent engineering, AI applications for semantic enrichment, storing models as objects in the cloud rather than as files, and linking data across models in that cloud. So let me just list these 4 things, because they're all aspects of research over the last 20 years, which have been explored and I would say matured to some extent, some more than others. Concurrent engineering is basically the idea that we can do things more in parallel than in sequence, with the reductions in duration, but also with improvements in not only in duration overall, but in efficiency, and creating less rework and less waste of rework when we design things that afterwards have to be iterated and changed. So we expect to have shorter development times, better product and information quality, lower development costs, and perhaps some enhanced collaboration. Now, semantic enrichment is this idea that you can apply AI tools to interpret and enrich semantic content in an automated way, so that models can, even on export or across domains, express their design intents and their intelligence in an explicit way so that software can read it. I mean, the thing is like this, that if you think about a BIM model, you think of any Revit model or Tekla model or MicroStation or Open Building or whatever software you're using, and you create a model, you generate geometry, you generate properties of those objects, you add that information, And you probably add some relationships because you have aggregations where, I don't know, a wall may have different layers. A room may be bounded by different walls and ceilings and floors and things of that kind. So you do have that, but there's another whole set of information that you don't model. There might be details with geometry that you simply take for granted that everybody will understand, or actually doesn't influence your design, or for whatever reason you don't model it. There's implicit information. There are implicit semantics as well. And then when you consider that there are different purposes of BIM models, maybe A is architecture and B is structural engineering and C is MEP, to use that triad again, then each of them, although you all may have the same geometries and all see that, you each have different understandings of the implicit information that's not there in the model. Like you take it for granted. And similarly, when you export in IFC, as I showed before, you have a loss of information on the export. And so when you import, you cannot recover that information. And so this idea of a round trip, when you get back into either BIM tool B or back into A, what you exported just simply doesn't work for those reasons of loss of information. But if you think about it, if any of you look at either of these the model on the right-hand side or the drawing, the cross-section of a model on the left-hand side, I don't think it would be too challenging. I mean, I think if we were in the same room, I would ask you now in the left-hand side, what is this? And you would probably say, well, clearly that's an apartment for people to live in. And then I would ask, well, can you identify the master bedroom? And hopefully most would say, yeah. Well, actually, I'm not sure you can see my mouse, but let's try this. Hopefully you say, well, yeah, okay, that's the master bedroom because it has this bathroom attached. Now, how do you know it's a bathroom and a bedroom? Well, only by the context. I mean, you can see this is a balcony and a living room, and perhaps here is the kitchen because we see the counter. And then that very quickly we understand what's going on in this apartment. Now, all of that information is what I'm suggesting is implicit. So to do a semantic enrichment would be to be able to use AI to identify that and to be able to say, yes, actually, this is the bedroom, this is the bathroom, there is a connecting door between them, and that kind of level of semantics would be added into the model. We've been trying to do this for some time. We had a project in bridge engineering, and we were able to create sets of rules that are unique rules that could identify components. This is a bridge pier that could identify the different components with fairly close to 100% reliability, and add those things in, add in relationships like what supports what, and what is aligned with what, and what are the intents of the design. So the idea is then very simply that you might be able to take an IFC file that does not have a lot of that implicit information, use an AI tool, and add that back in. And that's partly what I'll be showing in a moment. And then the next opportunity we have is that people have been working again for some time on the ideas. Here's a piece of work from Jacob Beertz, originally in Holland and now in Germany, but of having a BIM server where you would have it in the cloud, you would not have files but rather you would have objects. And those objects would be broken or delivered or served, if you like, to your own computer on your desk. And so you could bring down whatever objects you needed to work on them, and upload them back into the cloud. And that's mostly relevant from our perspective because we can break at least in your mind and the way that the software behaves, we can break the file constraints. We talked about this actually in the BIM handbook, and recognizing the challenge of object-based model storage in the cloud, equally at the same time recognizing that this requires sophisticated technology that well, we wrote this 2016, 2017, which now is becoming fairly practical in today's technology. But of course, it requires different BIM processes and software ideas. So one of those ideas is offered us by the work in linked data models by many people, including Peter Paulson's work I'm showing here. But here the idea is that we actually have clients, your CAD or your BIM system on the outside, and then a reflection of those objects in the cloud for each tool or each thing. But then in the cloud, you might have the objects in each domain linked to individual objects in another domain, creating this network of meaning which exists across domains and across disciplines and helps us do clever things. There are some examples of this, and there are the basic technology is there, not by any virtue of the construction industry, but by virtue of linked data technology standards and other solutions, which I don't want to delve into too deeply, but there have been prototypes of things like this VCon idea from Eindhoven already from 2015. So if those are our problems, and if those are the technologies that are available as tools in our toolbox to be able to begin to apply, then we can try to begin to imagine how next generation BIM systems might look. And what we really would like is that our BIM systems not just be modeling tools, but that they be indeed artificially intelligent, semantically rich, collaborative, concurrent, or supporting concurrent design, that the models within them be consistent in and of themselves, they be multidisciplinary, they use graphs. Graphs is our way of storing these things in the cloud and creating the linked data. And if we break that into technology and process, then there are 4 of these relate specifically to the way the technology works, and the other 4 relate to our processes and the way we design buildings and the way we think of design processes. So here, let me show you an example of a piece of research that 3 of our students have done here at Technion. And we, as an example case, we take this case study from a building built very recently completed here in Tel Aviv for Microsoft. And the building is a research center, development center. And one of the situations they had in this building was that they have these stairwells. There's a stairwell in the building. It has 2 doors, which are fire escape doors from the floor to go into the stairwell. And at some point, they understood that because of fire egress, these doors were not wide enough. And so the requirement was to make the doors wider. The stair here was a hard constraint, so they had to make the doors wider toward the wall, toward the yellow concrete wall that you can see here. And so the design change that the architects wanted to make was to move the wall, I think 60 or 70 centimeters to the left in this case. And you see then that the doors are now wider and the wall is moved. Now, what's relevant here is that in this model, there are sprinklers and many other things, right? But we'll just focus on the fire sprinklers. And so the fire sprinklers were positioned on the left-hand side. On the outside of that wall, there's a pipe, and then the sprinklers are all modeled in the wall. And if I flip it around, flipping 180 degrees, the model, you can see here that after they made the design change to the architecture, when they came back to look at the federated model, then this is what they saw, that in the federated model now, the sprinklers, the vertical pipe and the horizontal pipe, which are supposed to be attached on the outside of this wall, are now embedded in the concrete, which is wrong. So the challenge now is to say, well, how do, obviously we need to move that pipe outside. The design intent, as I showed you with the radiator earlier, the design intent is clearly that the pipe be mounted on the wall on its outside. So the situation we would like to achieve is to, ideally, the software would come along and say, oh, okay, clearly that was your design intent. Would you like me to move that pipe outside? It may ask people for numerous professions for approval, but at least they would just say, yeah, good, and we're all done. So that's the desired situation. So we said, well, okay, how can we do this in a software and build it and implement a demonstrator for this? And the way we do it is this. Firstly, in terms of the linked BIM, we consider that we're going to have a representation of the BIM models, not in a file in a Revit or whatever system, Well, we're going to have those as objects, individual objects in a cloud. And so here you see, again, I'm going to annotate here. You see this architectural wall object is a node in a network in the cloud, in the computing cloud. The same for the structural wall object here and this MEP pipe object here. And then we add into the cloud relationships that give us these equivalents. So we see that this architectural wall is equivalent to or corresponds to that structural wall. By the same token, we derive, or we understand automatically that the pipe, in a spatial sense, is located at some x-axis offset to the right of that wall. And going one step further in terms of intelligence, not only is that a spatial relationship between the vertical pipe and the wall, but we can also infer a design constraint. And that design constraint says that the bracket connecting the pipe and the wall must have a minimum value of 20 centimeters because we want to have space for inspection and maintenance. And that's in the X direction. So this constraint constrains the pipe to be at least 20 centimeters outside of the wall. Now, the first constraint is fairly easy to identify and supplement automatically because we can do geometry comparisons between the models. The other constraint requires that we infer an understanding the intent of the designers. So, yeah. So the way that we build this up, that solution is the following. We start with, if we look here on the left, an architectural model where we have objects in the architecture. And the first thing we do is we have a piece of software that can take this BIM model and transfer it into the cloud as a graph. And what you see on the right-hand side is here on the very right-hand side, an IFC column class. It's a type of object. And we have a particular instance, this yellow node at the bottom right, and that's column 253 in the graph. So we represent in the graph, in the cloud, what we have in the model with its geometry and with its names, properties, etc. And then we go to the structural model and we do the same thing. So now we're looking at a structural model, in this case in Revit, but it could be in any software. And in the structural model, the engineer has modeled this as 3 separate columns, because that's the way they'll be designed. They will have different reinforcement. They may even have different dimensions, unlike the architect who actually doesn't care about that. All they have is particular location really for a column. And so we see on the right-hand side in the corresponding structural graph, we see these three columns, which are of type IFC column, and they're structural columns. And they too exist in a different graph in the cloud, but in the same cloud space. So what we have now in this cloud space is we have an architectural domain property graph, and we have a structural domain property graph. And you can see that the architectural column A1 is there as a node, and the other 3 are there as nodes. They have a type and they belong to a type hierarchy, but that's not so important for me right now. What we want to do now is create the relationships between A1 on the left and the structural columns on the right. So if I present it this way, what we are doing is we're adding new nodes into the graph, and those new nodes represent those relationships. So you might have here on the left-hand side the A1, on the right-hand side the structural columns, and the node in the center represents a correspondence relationship. So it's capturing the intelligent relationship that column A1 in the architecture corresponds to these 3 columns in the structure. And by the same token, if I had a pipe here, in this case, a drainage pipe, outside of the column, I could do the same thing. I could have an MEP model with a node representing that pipe. And here too, I could have separate relationships where this attached to a relationship tells us that the pipe is attached to the architectural column and it's attached to the structural column. So I actually have now 3 different relationships: the pipe and its relationships to the different columns, and the architectural to the structural columns. Now, how do we infer that automatically? So mostly BIM systems can only process explicit semantics, and we have to make it explicit. And here we come to the semantic enrichment step. And there are two things we need to do. We generally need to classify objects, to identify that something is a column or a beam or a door or something else. And then we also have to infer the relationships between them, which is what I've just shown you between the different columns. So we first define what we call an ontology of those relationships. What kinds of relationships can exist? And it turns out that so far we have discovered three different kinds. Spatial relationships, which are topological. They say that one object is below another object, next to, in contact with, enclosed within, containing another object, and so on. And those relationships generally can be in any of the three primary axis directions. Those are all the spatial ones. The functional relationships have to do with things that serve one or another thing. So things can be part of another thing, a window being part of a wall, or a layer, a structural layer being part of an architectural wall. These are things that are functional relationships and then dictate how things behave. But then we also have constraint relationships, which generally express design intent, and they express the way that we understand buildings to work. So these are the kinds of things where within a discipline, we know that a window must be within a wall, but if it's across disciplines, it might be the kind of things we've seen where a pipe must be, or we intend it to be, attached to the outside of a wall. So the first step in implementing this stuff is to outline this ontology. And so we have elements, we have relationships. And as you see here, the relationships break down into spatial relationships, which may be topological, offset, or in contact. And then we also have constraint relationships, which may be connections, they may be design intents, they have directions, they have operators, and they have values. And so this lays out the different ways in which we understand that information to exist. Once we have an ontology like that, it's not hard to write the software to apply those things. So let me give you an idea. So what we're doing here is we're taking the models, the individual models, we're uploading them or creating copies of them, if you like, in a graph structure. So there is a discipline graph. Outside of that core graph, we're also maintaining some of the geometry and other things in our common data environment, which are cumbersome to put in the graph. So things like solid geometry is contained in solid geometry files related to each object. And then we're inferring these meaningful relationships between the objects across the different disciplines. So we're suggesting that this new representation of linked data in a common data environment is a way for us to present multiple disciplines in BIM. So how about if we want to now use, how do we actually do the inference? Oh, excuse me, I'm here to, yeah. Well, we do the inference by saying that this CBIM database is our cloud. We have in the orange and green, we have tools to create the relationships with our individual domain-specific software. So an architect, an engineer, and so on might have their own very discipline-specific interface into this cloud. And then we have a whole set of a GUI with consistency maintenance, version control, simulation, generative design, semantic enrichment, and other object-level cloud communication functions that operate directly on this database in the cloud. And it's these blue things that provide us the additional intelligence that allow us to fulfill those scenarios that I showed you. So let me show you how, there's a publication about this, but here's the kind of things that we would like it to do. Imagine here on the left, an architectural model, in the middle, a structural model that corresponds to that architectural model. And on the right-hand side, we see the violations of our design intent. And there are obvious ones here. Intentionally, I take obvious ones, but what you're seeing here is a Boolean intersection operation. So you see that this column and the two beams in either side of it, they interfere with that window. Now, clearly our design intent is that the concrete column should not sit in the middle of the window. That's exactly the kind of design intent that we understand, actually. And the same thing on the right-hand side, where the beam intrudes and conflicts with the window. Now, in current practice, we would have to wait for a federated model and then a clash check, and we would find that out. They're a lot more effective if we could avoid that to begin with. So can we define that kind of design constraint, design intent in a mathematical way? And really what we're trying to say here is that structural model elements in a building superstructure should never protrude from their corresponding hosting architectural model elements to avoid unintended structural exposure. And if you want to say that in a mathematical form, you could say that the structural model element geometries in Boolean form, when subtracted from when you subtract the architectural objects, you should end up with an empty set. So there should be no structural geometry that can remain after you do a Boolean subtraction of the architectural geometry. And that can be applied to the whole building, but it can equally be applied to sets of objects like a building's facade or its floor. And design intent number 2 here, we express the idea that architectural slabs that make up the floor of a story should always be supported structurally throughout their horizontal extent. But we don't want to have a model with a structural floor which has no structural support. And by the same token, we don't want to have structural supports in areas where the architect doesn't require them. And that breaks down. And again, you can express this as the set of architectural elements that create a floor on a particular level of a building. When you subtract all the structural floors from them, should have an empty set as a result, because we don't want any architectural elements that have no structural elements supporting them. And it turns out that you can create these kinds of mathematical Boolean expressions to give meaning to these design intents for quite a number of cases. And if you can do that, then you can begin to express them in software. And I won't take time on this. I know that we're coming to the end of our hour, but they are in the paper, but I'll explain to you how this works. So we're able then to use those things to write rules that can determine these situations. And now you see how it plays out in the practical example. So you see on the right-hand side an architectural subgraph of a single room building, idealized kind of building that you see here on the right. And in the green, within the orange rectangle here, you see the subgraph of these different objects, the walls, the floors, the ceilings, and so on, the window, the door. On the left-hand side, you see the same thing for the structure with the structural model and its graph components. And then in between, you see the relationship objects in the metagraph, which represent those relationships. So you can see that some of them are spatial, some of them are exact geometry spatial, some are relationships that have correspondence, and some have subject and object where they represent design intent. And so let me show you how this plays out now if I make a change. So if an architect in their client software decide to move one of these objects, like let's take the wall on the right-hand side and decide to move it to make the room bigger, well, that should, in an ideal world, automatically have the impact on the structural model that the structural engineer should receive a notice and say, oh, the architect would like to move that wall such and such centimeters to the left. And actually, because that wall is contains or is implemented by this frame that consists of 2 columns and a beam, then actually that frame should move an equivalent distance to the left. And if that happens, then naturally the ceiling slab and floor slab should move with them, because equally the architect has extended those slabs and there are equal design intent relationships between the floor and the slab. And that's exactly the kind of change that we are, and we've been able to demonstrate by creating prototypes of this kind of software. So in summary, I guess what I'm trying to say here is that if we're able to add in much more semantic meaning into our models and create that semantic meaning across disciplines, and we're able to capture all of that in a cloud representation of the whole model, but not as files, but rather as individual objects, then we can achieve much more collaborative and concurrent design paradigms. And that requires us to have knowledge graph representation. It requires linked data. We need to have an ontology of all the relationships and the design intent connections. All that what is all today implicit needs to become explicit. And we need to have an additional layer of intelligent software that can apply and suggest corrections when we violate those constraints that we know to exist. The benefits are numerous. Some of them I'm listing here, but we might be able to make clash checking obsolete, because maintaining model consistency would be a more natural thing, in the same way as an architect doesn't need to consciously maintain consistency between windows and doors and walls. We can extend that logic across all of our models. We may be able to have concurrent work, advisory agents. We could have more intelligent design agents suggesting different things. We might have advisory agents reporting real-time code compliance violations and things of that kind. Much easier to do that when you know information across disciplines, and so on. And so what I'm suggesting is that as research goes ahead, and as these things will become more and more adopted into technology and vendors will implement them, we are likely to see much more artificially intelligent, semantically rich, collaborative, concurrent, consistent, multidisciplinary graph and cloud technology in BIM. And so I'll stop there and perhaps open for broader discussion.
Thank you, Rafael. Such an impressive presentation. So now comes to the Q&A session, and we're open for discussion. Anyone from the audience would like to ask a question? We could have 15 to 20 minutes. Yeah, just feel free to unmute yourself and speak directly.
May I go first, or?
Yeah, you're welcome.
Yeah, okay. Well, yeah, because I'm sure Robert will make a more difficult question. So I go first with the easy one, because, you know, I'm still learning about all of this. And I just wanted to say that it is an honor for me to be here, Professor Sachs, and with all the Professor Robert as well. So a little bit just introducing myself. I also a lecturer here in New Zealand and at Massey University, former PhD student from Georgia Tech. So I had the pleasure to attend a few courses with Professor Eastman, and very much interested in this topic, although that's not my main research topic at the moment. But I was just thinking, if I understood it right, the knowledge graph you mean, and you showed us the knowledge graphs, are they ontologies?
Let me go back and make sure I know which ones you're referring to. Zenanga, I turned off the sharing, and I see now that it's restricted to host only. Can I share? Oh, yes, no problem.
Well,
sorry,
it's actually, my question is,
yeah,
actually has to do with the ontologies, where you start talking about the relationship, the nodes and relationships to define an object in this new language of an ontology. And my question is actually in the design of the ontologies, in the translation from the implicit to explicit knowledge, as far as I understood, it's still somewhat based on expert knowledge, right? So
Absolutely.
we need professionals to say, oh, this is a window, and a window consists of this, this, and that, right?
Yeah.
And this expert knowledge, of course, is based in turn on how we currently build buildings, right? How we currently construct things. My question is then, how could that be impacted, the design of an ontology, right? How could it be impacted by the possible diversity of design principles in different typologies of current and future buildings, right? Like, I'm an architect as well, so that's a question from an architect. Let's suppose I want to design something that somehow violates the rules of the ontologies. And to what extent, my second question, which is related to this first one, to what extent would that be limited, right, by the generation of a new logic architecture? How would that limit the architectural design?
Right. Okay, superb question, because it allows me to take this just one or two steps further. Okay, so what you're seeing here is a set of instances. So in this slide, you're seeing instances of objects, nodes that represent objects, you know, on columns, structural columns, and architectural objects. And then in between here, these are nodes representing concepts that are the relationships that we're talking about. Some of them are the design intent relationships. And those are all defined in terms of their class belonging by this ontology that I showed before here. So, and this is not the last version, and it's a work in progress, I should add. So don't see this as something final. But the ontology represents that set of understanding of relationships, both spatial, topological, and design intent. Now, you put your finger, I think there were two really good parts to the question, because the first is, how do we know what those design intents are? I mean, before we can infer them in any given model, we have to characterize them, classify them, define them in the ontology. So we have to derive them from somewhere. And you're absolutely right that at this moment, the main source that we have used from them is expert knowledge. And expert knowledge right now translates to our experience as architects and engineers, and our understanding of how buildings work. When I say our, I mean our research team. The next step would be to go beyond the research team, perhaps, and do a sort of an knowledge elicitation step. But we know from expert system research through the 1980s, 90s, early thousands, that that's really very challenging, and that different people have different kinds of expertise. And not only that, but many experts are finding it very difficult to express their understanding in ways that can be computerized or that can be expressed in mathematical expressions. So while I do think that that will remain the main way we do this for some time, because a lot of those design intents are fairly easy, right? Like the fact that the structural frame on the front of a wall fulfills the goal of structural support of that facade. Those are relationships between architecture and structure that are very well understood. By the same token, if I had a pipe penetrating a wall, and there's an opening for that pipe to go through a concrete wall, then the relationship between the hole or the penetration, the clearance, and the sleeve, if you like, and the pipe is obvious. We need the sleeve to be placed where the pipe is. So if a mechanical engineer moves the pipe, we like the sleeve, the opening in the concrete, to move with it to maintain that function. So those kinds of functions are obvious. When we get to more complex things, then we're currently trying to figure out if we can use deep learning approach. That is to say, if I were able to accumulate a good number of, let's say, architectural and structural model pairs, and I was able to label the objects within the domain, right, not the intent, then could I perhaps find, because we already are able to annotate the topology automatically, so we can add in all the topology relationships and the geometry relationships. And then we could say, okay, now we have a very big set of architectural structural models with cross-domain relationships. Can we do a clustering or a deep learning exercise where we identify groups of relationships that recur again and again? And if so, could we then present them to experts and say, oh, we see that in all these 1,000 models, the pipes run through the sleeves. Is that an intentional thing? And then they might say, oh, yeah, okay, that's our intent. So we may be able to get a lot of design intents in that way. It will probably be, you need to have certain types of buildings, and there are a lot of caveats, but it's a start of a direction that we're exploring. There are increasingly more and more models available to do these kinds of exercises with deep learning and with machine learning. Mm-hmm. So that's one exercise. And the second question you asked was, which I also like, if we apply all these constraints, will that restrict or constrain architectural design in some way? Well, I think that question is similar to the question, do current BIM systems constrain my architectural freedom or creativity in some way? Yeah. And clearly some of them do. I mean, if Revit was the only thing I had for design, then presumably I would, over time, develop Revit-looking buildings. Mm-hmm. But I think that we architects know when to turn on or turn off, if you like, the functionality that the software offers, to merge with systems like Rhino or others that give you a lot more geometric freedom, perhaps, and also to invent new architectural forms that have different relationships in design intents than things we've had in the past. And so I don't think that that's an absolute constraint. I think that will have impact in early conceptual schematic design. It may also mean that we need to maintain designers' control. So we're not ever going to make automatic fixes, but we are going to say, wouldn't it be nice if I could do this for you? Would you like me to do this fix automatic for you? And allow the architect to say yes or no, or yes, but change that, and then it gets done automatically. So the system should function more as an assistant or an intelligent assistant, or a junior architect or an intern, rather than the authority. And the final thing I would say in that is that most of what we're pushing toward is to reduce the drudgery, reduce the technical work. One of our PhD students in Helsinki, working for Trimble, did a survey which had over 230 responses, and asked what were the main issues that people found with their BIM workflows, not with the software, but with the workflows. And the challenges of maintaining consistency across models turns out to be one of the major headaches that's requiring a lot of time and is the source of many, many errors. So at that level, it's much more technical in nature, and we could imagine much more automation, I think. I hope that answers.
Yeah, of course. I guess we can sort out 99% of all problems we have, with this kind of solution. Yeah, definitely.
Yeah. Now comes the hard question. I saw Robert.
Always ready.
Do I have to? Hi, Rafael. So I guess over the years, I've been a bit of a Luddite about AI and what it's able to do. And but more recently, I've been impressed and scared by what tools like GPT-3 and others are able to do in this area, in all areas of science and engineering and architecture and arts and almost everything they've been applied to. And I guess my question is, I wonder if those sorts of tools actually skip this process that we have, the need for ontologies, the need for deep insight into the domain that we have, and through the statistical approaches that they have, actually give us solutions which don't need us to be able to model and understand our domain in this sort of detail. And I'll give an example. From computer science, we've just been analyzing what GPT-3 can do on all of our exams, our first year computer science exams, and GPT-3 gets an A- basically
Not
it can
bad.
take any of our questions that we have in our exams and generate computer code to answer those questions at a A- level for our students.
That's
And you know, and we've seen this. It's been tested in many domains, and is able to produce results which are incredibly believable and understandable. And so, you know, for us, the question is, you know, do we need to understand and model the detail in these areas, or are these tools really going to take us to the next step without having to have all of these sorts of models and constraints and understanding of our domains?
It's a great question. I mean, of course, I cannot answer that even remotely intelligently. Maybe you want to pose that question to GPT-3 rather than to me. But seriously speaking, I think that one of the reasons that tools like that are able to make progress is that they do have access to vast amounts of data. And they have access to computer readable and interpretable kinds of data. I can only assume that in the example you gave of exams, that they have access to vast amounts of computer code and are then able to match code to purpose and firstly interpret the purpose that you're looking for in the question, and then find something that addresses that, because it's been done in the past somewhere, sometime by someone, and it's able to dredge that up. The same goes, I think, for chatbots and other things, where they're heavily dependent on very vast amounts of prior information or prior data. And I think that as we continue to build BIM models, and as companies continue to be lackadaisical about their security, and so those BIM models are more available to crawlers and so on the web, then we will see compilations of very big sets of data. That data might need to be augmented first with these kinds of relationships, but some of them can be done automatically. You know, certainly the topological things and the offsets and the contacts and all that. These things can be done automatically. So you could then have a slightly enriched set of data. It's not unlike that you might have text, and then you're able to label the text, you know, as speech parts in automated ways. And that's just the first level of intelligence. Then you build the next one until you actually can understand it and respond to a request or a thing. So I think it's a creeping, it's a progression, and we're only at the beginning, not because the AI tools are too weak, but because we don't yet have the vast amounts of data available in formats that can be used, and perhaps only because AI developers have not paid enough attention to our domain. It's challenging, I think, for you and I, and many on the call, as researchers who are in this area of BIM and AI, or BIM or civil engineering architecture, to understand that we may be eclipsed by computer scientists and or AI developed by computer scientists who, yes, may be able to do more deep learning as time goes on, and yes, interpret intelligence from these things, infer intelligent relationships, and then build layer by layer until they're able to design buildings. It's hard to see why not. But it's all speculation, I suppose, at this point.
Yeah, I guess in New Zealand, I don't know, in all other countries, everything that gets submitted to the councils for code compliance checking is made publicly available. So every building in New Zealand which is compliant is available on the internet somewhere. So, you know, so if other countries are doing the same sort of thing, there is actually quite a large resource of compliant buildings, which these AI tools are able to walk over and try and statistically infer what is good and what is not.
Yeah, exactly.
I was interested in one of your very first slides where you're talking about, I guess, the kind of revolutions, through to CAD and then through to BIM. Do you see those as kind of incremental steps, or do you see them as revolutionary steps? And I guess if you see them as revolutionary steps, what do you see as the next revolution after BIM?
I think that, you know, in any kind of product development of this kind, there are incremental steps and then there are major steps, paradigm changing steps. And I think that the move from certainly the introduction of the stuff, the descriptive geometry and the parallel projections, these were major steps in terms of human understanding and tools, development of tools. It's not unlike developing a car or something like that. But then things develop slowly with additional improvements, bit by bit, incrementally, until you come to the next major step. And the next major step, I think, is not CAD, but is BIM. And in the sense that CAD took computer tools and applied them to make descriptive geometry and parallel projection better. But there was no real paradigm change. We still produced drawings. We still produced cross sections. We still produced perspective views, just we did them faster and more reliably. But building modeling was a paradigm jump. And then perhaps that's why it's actually taken much longer to spread through industry than we thought, because when we consider modeling things as objects with all their information, that's completely different from having a representation of them. So the jump from everything, descriptive geometry and CAD to BIM meant that we could now create actual prototypes of our buildings in the computer, prototypes that could be simulated, could be emulated even, and that we could use to predict performance in the way that, say, mechanical engineers could produce a prototype car, crash it against a wall a few times, and understand how it's going to behave. That's the kind of thing we could never do before. With good computer BIM models, we can do those sort of simulations, and that's a paradigm change. The kinds of things I showed now are perhaps not paradigm changes in the sense that they will improve the way we collaborate using BIM. But it is a creeping paradigm change in the sense that the more we add layers of intelligence, then we will get to the points you described with the GPT and ability to take exams or write or create artwork of 19th century masters, or write novels, and that clearly would be a paradigm change.
Great. Any other questions from the audience? If you have a question, you can just unmute yourself and speak directly. Yes, Zu, I see you raise your hand. Do you have a question? Okay, I think that should be fine. So I think, yeah, so very impressive presentation. Once again, Rafael, I think.
Sorry, I have probably got a quite late question here. My name is John Jiang. I'm one of the PhD students from Auckland Uni. I'm in the actually the BIM application area. That's my research area rather than BIM itself and the design. And one thing I'm really interested in from your, I think the presentation is the semantic enrichment. So I'm working on very similar kind of a concept, but in the BIM application in terms at a different maturity levels, which means you have to enrich your data in terms of your your graphic attribute and other non-graphical attribute, so you can deal with a different level of the decision-making maturity levels. So that's very interesting and definitely very helpful. But my question actually is that because we're talking about the trend of BIM in the future or near future, or long-term future, is that we see a lot of this, the game engines like Unreal, Blender, or any others, and they are trying to get into this the engineer field, put it this way, and they're doing lots of like the digital twins, and we see BIM model, like the Rivet model, they been exported to this game engines to make all these real things. So my question is, what do you think that how there's two different areas, like one is engineering area, like the BIM, and another one is like a game area. So and you can see the impact from the game industry, because they have the ability to influence for all other areas. So is that a kind of thing they could get more involved into this engineering area, or any other trend that you can see between these two areas?
Not right away, not so immediately. We just had a week ago, there was a conference in Tel Aviv called Construction 4.0, which was a gathering of construction tech companies from around the world, but mostly from our local ecosystem. There are maybe 150, 200 construction tech startups in the Tel Aviv area and around here. And of all the things that they're bringing, there wasn't even one that had to do with gaming technology or with advances to BIM. And that's interesting because we have here an Autodesk Development Center, we have a Trimble Center, we have others. And most of the technology developments that relate to BIM have to do with better use of the information, closer integration of scheduling and estimating with BIM models, things that are not necessarily new in research spheres, but are new in implementation for the construction industry. And I expect that if there were already crossovers of game engines being applied for construction or for design, then we might have seen them. We do have examples of 3 or 4 companies who are doing automated designs, who are doing parametric designs of various kinds, applications within BIM. But I honestly didn't see any, there is a huge industry of renderings and architectural renderings which use game engine graphics tools. And I suppose that will increase. But personally, I'm not aware of any direct contributions that are impacting the area we're working in. Not yet, anyway.
No. Yeah, I think that's I have a very similar observations. That to say, there's not much that happening at this stage, but right. We can't see in the future. Right. Maybe they use a Blender to do to set up right. models and put all the information in there, and use it for our analysis. Whatever the design right. analysis.
Yeah, I think there is one area where it might change. Is that if you think about the commercial development now, in parallel with the technology development, if what I've described as a cloud graph model at the center as the federating model, which has both domain models and the federating relationships across them, if that becomes more strong and accepted, then you could see a future technology situation where the individual domain tools like Revit or Tekla structures become less relevant because they're not the central tool, they're peripheral, or their interfaces into the main database. You could even see companies coming up with new clients that simply use the central model as their data store and have no independent data store. That may happen if they are able to have schema for the graph model that do represent the domain design intents as well as the cross-domain design intents. Now, if that were to happen, you could easily imagine clients, BIM clients based on game engines like Blender or other Unity or others, where you have the geometry really well done, that provides you an interface into your federated model on the cloud. That could happen. And then I assume that rendering graphics technology would be supremely important and may, in some senses, either displace the major vendors or force the major vendors to uptake that kind of technology. It's not unlikely that, again, from a commercial perspective, that you would see some sort of startup company doing that, developing an interface into a cloud graph-based model and being successful with that, and then, of course, being acquired by an Autodesk or a Nemetschek or a Trimble in exactly the same way that when Revit became a threat to AutoCAD, Autodesk simply bought it, lock, stock, and barrel, and then became a BIM company as opposed to a CAD company. So the technology clearly, I think, will have an influence. Whether the industry or the companies will have, that remains to be seen.
Yes, I totally agree. I think it's probably outside the scope of today's discussion, because when you look at the market value or the capital value of the game engine company versus the other the BIM like Autodesk or other companies, probably one day you will see they could probably can be merged into one of those the game engine companies. Yeah. Thank you.
Sure.
Okay, sweet. So, Rafael, do you have a minute for the last question? I just received another question from the audience in the chat box of Zoom.
Sure, if it's short.
Yeah. So, Fahad, one of the audience, he's working in an architecture firm, and his questions about what's the obstacles hindering the implementation of BIM process in architecture firms. And his original question is in New Zealand, but I think you can change it to what's the obstacles hindering the implementation of BIM process in architecture firms in Europe.
Yeah.
So what do you think?
Or
globally or internationally? Yeah.
You know, I'm not an expert in this, and of course we've considered this, and there is some text in the BIM handbook about barriers and how to overcome them and so on. But I'll just be brief and make only one observation, and that is that where companies have individual people who are able to master the technology and who are able to get the maximum out of it, there are actually very few barriers to them using it to really powerful effect. And so you see both within very big companies like SOM or HRK or Zaha Hadid or Foster, and you see uses of BIM that are truly spectacular, and the result is you see buildings and projects that are really wonderful. But by the same token, you can have one-person firms or 2 or 3 people firms who are able to use the technology, and maybe they don't do entire buildings and so on, but they complement officers doing the more drudgery work, and again come up with exceptional work. So yeah, you can find in the academic literature and in the popular literature lots and lots of articles about the barriers to BIM. They have to do with low profit margins. They have to do with very low capitalization of design firms. And design firms tend not to have a lot of capital, so they don't make long-term major investments. Cost, training of people, and so on, all these different things. I think they're pretty standard across the world. But one thing to recognize is that it's one thing to talk about star firms or star architects and so on, and engineers doing things. It's another thing to talk about a whole industry moving. And whole industries are very complex systems. And so they're very dependent on a very wide variety of players. That may be from suppliers of materials, fabricators of steel, fabricators of concrete products, suppliers of doors and windows and so on. And for an industry and a country to move toward working with BIM, it requires a critical mass of all of those different players to do the same thing. And that simply takes time. And I don't think it's anything more than removing a lot of small barriers one by one, and then eventually you get an overall effect in the country. The UK has been exceptional in that any country that has a BIM mandate from government for major suppliers has a big impact on the industry and can make things move a little quicker. But it's not a fundamental difference.
Yeah, thank you. Yeah, so on top of your answer, so to answer his original question, what about the BIM process in New Zealand? So just from my observation here, we still don't have the government mandate in terms of BIM implementation, so still far behind in the world. All right, so I think
actually we do have a government mandate, so it's not very well known, but the government actually has mandated that BIM be used on all government projects in New Zealand. So that has been in place for over a year now, but it's hidden away in some of the government documents, but
Yes,
it is required in New Zealand.
I
Yes,
thought
I
it's
agree.
for healthcare, for Ministry of for healthcare facilities or Ministry of Education.
Yeah,
Right.
there's a mandate for all the government the major capital works for the infrastructure list, that you have to use BIM as a part of your design and
For-
the delivery. Yeah.
For public projects, right?
Yeah, that's only for public project at this stage. The requirement here.
Sweet, thank you. All right, so we are running out of time of this seminar, and once again, I would like to thank you again for this very impressive presentation, Rafael, and we hope we can host you here in person in New Zealand. We are very remote from the world, but if it's fortunate, we can invite you here.
Thank you very much. And thanks for organizing the session.
Yeah, thank you. Thank you for your presentation.
Thank you, Professor.
Bye-bye. Thank
Thanks,
you all for
Rafael.
great questions.
Yeah,
Bye-bye.
and thank you for everyone attending this session.
Thanks, Fang.
Thanks, Robert. See you.